Yeah, so it's 7 o'clock now. So let us begin with today's class. So I'll be just sharing my screen now. Is my screen visible? Can you guys reply on the chat box? Okay, thanks. Okay, so good evening everyone. So my name is Sumant. I am a PhD research scholar in Department of Mechanical Engineering at IIT Bombay, and since 3 weeks we are having this tutorial sessions on the introduction to CFD course, which is AE20, and this is week number 4, the today's tutorial sessions. Okay, and today's sessions is based on numerical solution of steady state heat conduction problem mainly. Okay, so I hope that all of you uh, have gone through the weekly contents. So this was week number 4. So this was mainly based on solving different equations and through different schemes. Okay, so let me make quite few announcements. So first of all, these are just tutorial sessions. Okay, so these are not the actual theory sessions. So all of you are expected to go through the weekly contents. That would be more appropriate before coming to this tutorial class. The main intention of these tutorial classes is to give you a practice on the problems which you encounter in the CFD course, so that you become like better with respect to what is being taught in the weekly contents. Also, that was just the first objective. The second objective is to help you to kind of easily solve the assignment questions. Let me be very clear. We are not supposed to solve the assignment questions. Okay, problems which are similar to your assignment questions will be solved. Okay, so if you ask me some particular assignment questions, then I cannot give the answer for that particular assignment question. But if there are some similar questions, maybe we can discuss. Okay. Yeah. So that is the main intention of conducting these classes. I hope I am clear with this. Okay. So let us just begin with week 4 contents now. Okay. So but before going to the recap of week 4, can you guys write down on the chat box what was mainly covered in week 3? What were the main contents which we saw in week number 3? There were mainly two components. Can you write down on the chat box? So in the first class we had seen into what is CFD, what are its application areas, and what is the basic math which is required in week 1. Then in week 2 we slowly entered into the partial differential equations which are encountered, and what are the different governing equations which we deal with which we deal in this CFD. Okay, and what did we see mainly in week 3? Can you guys write down on the chat box, please? Okay. Taylor table wave number in week 3. ST Bindu is modified wave number. What about others? Feel free if you kind of mix up also with week 2, that is fine. I mean, sinusoidal functions for what? Uh, Let me be more precise. Like, why did you consider sinusoidal functions? Yeah, modified wave number. Okay. So why did we use the Taylor table? I mean, for what purpose did we apply it? What was the main intention? Can you write down on the chat box? So again, let me give a brief timeline. Okay. So we started with the governing equations in computational fluid dynamics in week number 2. Okay. So mainly the steps followed are, first you create the geometry, then you kind of discretize the domain. Okay. That is the main thing which you do in CFD. Okay, discretize your governing equations. Sorry, discretize your governing equations, and then once you discretize them, you have to solve them. So we had just dealt with governing equations in week 2. In week 3, we mainly saw how to discretize. Okay, we saw how to discretize them. Okay, so we used Taylor table approach for that. Okay, okay. So I have got some responses. Any order of differentiation can be written with desired accuracy order of it. Yes, exactly, Divyendu. So in week 2 also we had briefly seen how we can use Taylor series, okay. But then in week 3 we saw that if we have more number of stencil size, then this Taylor series doing the manipulations becomes very tricky, and that is why we saw how we can use Taylor table approach to come up with a finite difference approximations. That is, we wanted to convert the partial differential equation, for example, dou square f by dou x square you have. Now you have to convert it into a discrete values, okay, discrete function values. So discrete means at different grid points, okay. So you wanted to approximate dou square f by dou x square with some fi plus 1, I minus 1, and the grid step size delta x, whatever is there. Okay, so that is mainly called as discretization. So you want to solve these equations in computer. Okay, but the computer cannot directly solve the partial differential equations. Okay, so you need to feed it in the form of some algebraic equations which are mostly linear. It can be non-linear also, but mostly linear is quite easy. So you want to convert them into some linear equations. So that is the main objective of coming up with this Taylor table approach, to find the discrete formulae for the partial differential format. Okay, so that was the first step. Okay, now you saw how to kind of come up with this discrete functions for partial differential equations. Now, what is the next challenge? Okay, and also you saw modified wave number to kind of measure the accuracy of any scheme by seeing how the modified wave number compares with the actual wave number. You can decide at which grid size the accuracy will be lost. So for that you use wave number. Okay, so I had asked you a question now. So you have now discretized the equations. Okay, I mean you have arrived at discrete function values for dou square f by dou x square, dou square f by dou y square. What is the next step, which is relevant to our week 4 discussion also? What is the next step? Can you write down on the chat box? After doing the discretization, what is the next step? So you have equations, right? You have now you have equations which are to some extent algebraic equations. They are linear. Okay. Now what is the next step? Okay, determine the value of desired function at the grid points. Yes, very good. So that is the major challenge which is there. Okay, so you have come up with algebraic equations, but how do you solve them? How do you make the computer solve them? It's more necessary to understand how you make the computer to solve them. See, partial differential equations you yourself can solve without doing discretization also. Okay, you can do integration. I have dou square f by dou x square is equal to q, say. Then I can say f is equal to qx square by 2 plus c1 x plus c2. But computer cannot do that. Okay, so that discretization and then solving, you need to understand it because you have to later program them. Okay, you have to write the programs for this, so that is why you need to understand this, and this is the most important thing I would say. Whatever the content has been covered till week number 4, this is the most important things. These are the most important things in CFD as far as my experience goes on, because mostly if like people are not very much strong in these things, then the remaining things, even if you understand them, then you will struggle to write computer programs. Okay, because you have not understood these main things. So especially I would say week 3 and week 4 contents are very important, because you learn how to convert a partial differential equation in discrete functions, and then you understand in this week, in the week number 4, you understand how to solve them. So discretization, there are different methods you can learn on your own or through different course also. But these things preliminaries are very important. Okay. So I would suggest please sincerely go through this week 3 and week 4 contents if you are not gone through. Okay. Then try to sincerely attempt the weekly assignment questions also. Okay. That would be of a very great help later on. If you get into some I mean software companies also which kind of develop CFD softwares. For example, you have ANSYS, you have MSC, you have COMSOL. Okay, you have many softwares, many companies which develop these softwares. Okay, so they need people who can develop these programs. Like for example, see, they have already developed the program for CFD. I mean Navier Stokes, it's already done. Okay, but if they get a new physics, some transport phenomena comes in. Okay, or some new multi-phase things they are doing, or some multi-physics. Okay, fluid structure, fluid acoustics. So they need people who can kind of come up with computer programs to solve these physical models. Okay, so at that time these things becomes very important. Okay, these are like the foundation stones, I would say. So yeah, that is the main suggestion. Please go through these things very carefully. Okay, this will help a lot in your career. I mean, if you are going forward with a CFD career. Okay, because this has been my personal experiences. I'm telling from my personal experience. Without these things, going ahead will become difficult. Okay, okay, yeah. So we mainly saw steady state solution in this particular week number 4, and can you guys write down in the chat box what is the main significance of the steady state solution? What does it indicate basically, the steady state solution? See, for example, I have flow in a channel, a fluid flow, water is flowing inside a channel. That is my problem. Okay. Now I come up with some steady state solution. Okay. Okay, or else let me make it more simpler. You have just a 2D metallic slab. Okay, and then you have some 4 fixed temperatures on all the boundaries. You get a steady state solution. What does that indicate? What does the steady state solution indicate? Can you guys write down on the chat box? See, you get finally some values of temperature ultimately. Okay, but what those values indicate, like let me make it more subtler. Okay, see, if you are getting some solution, does that mean that the metallic slab immediately reaches that particular values of temperature, like immediately after providing four different temperatures at the boundaries of the metal? uh, okay, once we change boundary condition, it will immediately reach the another equilibrium. Yeah, that is correct. Solution at equilibrium. Okay, so what I was trying to tell is that you have a 2D metallic slab and you have four different temperatures at four different boundaries, the north, south, east, west boundaries, okay, of the full metallic slab. Now what I am asking is, what do you get from this steady state solution? Is it like immediately after you enforce those four boundary values, you then directly get that in a physical situation, or something else happens and then you stay at steady state solution? Okay, so some people have answered anyways, that is correct. Solution at equilibrium, and yeah, we change the boundary condition, the result will also change. Yeah, but the main thing is, these are the equilibrium solutions. See, what will happen in reality is that the temperature will slowly change inside the domain, and then it will reach to one point wherein the temperature stops changing. Okay, so if you compare CFD with a video camera, okay, video camera like a tool. Okay, so you are assume that you are taking video of one particular process which is happening. Okay, so like for example experiment, you are trying to capture the flow of water in a channel, okay, through some camera. Okay, so and you are trying to make a movie out of it. Okay, so what happens after some times is that the movie stops changing. Okay, the scene remains the same. Okay, it becomes static, it becomes only a photograph after some time. So this particular point, this particular solution where it becomes a photograph, that is the steady state solution. Okay, yeah, transition part cannot be determined, only one equilibrium to another equilibrium. Yeah, so in steady state solution you are not looking at the transient things which are happening. So when you capture it using a video camera, like as I told you, flow of water inside a channel, you kind of capture the transition also what is happening. Okay, so but here you do not capture that in a steady state solution. We will later see in the next weeks maybe that we can try to capture that also using the transient simulations. Okay, so that is also possible, but anyway, so these things are not possible with steady state solution, only the final state is obtained. Okay, so you saw mainly two equations, Laplace and Poisson's equation, okay, in this week. And one more very important thing I would say, which will continue for the rest of the course, is the grid nomenclature. So you saw that in the x direction you gave I index, and in the y direction you gave j index. Okay, so keep this in mind, it will remain constant for the course, full course. Okay, it is similar to your I hat and j hat. So I you give in x direction, j you give in y direction. If you have a third direction, you can give k hat, sorry, k index. Okay, and then you also looked at the second order central difference, fourth order central difference. Just a brief recap, we are mainly using these two to obtain the solution. Now this was about the equations, how you kind of discretize the equations, which schemes you are applying, everything. Okay, about steady state solutions. What was the main other thing which you saw in this week? That is mainly how to come up with a solution. Okay, uh, different solution algorithms. What were the different solution algorithms? Can you write down on the chat box which you saw in the week 4 contents? So we have come up with linear algebraic equations now, okay, using our discretizations and grid nomenclature, everything. Now we have to solve them. What are the different algorithms Jacobi, Gauss Seidel, TDMA, ADI, Gauss. Okay, fine. So you guys are telling only one particular thing to me. Okay. So now you have, for example, AX is equal to B matrix system. Okay. So now you ultimately want to find the value of X. Okay. This whatever algorithms you are telling is just one particular scheme. Okay. It is basically an iterative scheme. Is there anything else which we can do? I have given you already a hint. These are iterative schemes. What is the other main category of scheme? Okay, we can divide it into two parts: iterative and the other part. In iterative, these algorithms comes Gauss Seidel, Jacobi, whatever you are telling. Okay, and TDMA also you have used for line Gauss Seidel, I think. Yeah, but TDMA comes in the other part also. I would agree with that. Yeah, exactly. Direct solution using inverse matrix. Yes, one approach is directly calculate the inverse. X is equal to A inverse into B. Ultimately, you get the solution. MATLAB can calculate the inverse very easily. Okay, but why don't you do that? That's the question. That is so very easy, cool thing. Okay, why do go for iterative schemes? Why cannot you just directly do X is equal to A inverse into B in a computational setup? Can you write down on the chat box? I mean, why are the iterative algorithms really necessary? See, if the number of grid points increases, computational size increases. Okay, okay. Computational time is large in inverse matrix discrimination, convergence. Yeah, absolutely. Both are correct answers, I would say. Good. So computational time is large. Yes, very large. If you go with a larger this thing number of grid points, larger number of grid points, if you take inverse calculation, just not possible after some limit. Okay. And then convergence. Yeah, convergence also sometimes you face an issue with the if the matrix is A is indeterminate or some issue is there. Okay, so yeah, that is also an issue. Now, if we see iterative schemes, they provide reasonably accurate solutions. Okay. Now again, if we see when we are doing the inverse, okay, we get accurate solutions of the linear algebraic equation. In iterative schemes, we get approximate solutions of the linear algebraic schemes. This is very important. Okay, you have to understand it. We are already doing some approximations while doing discretization. You will end up with truncation errors. Okay. Now, along with that, there is solution error also. Okay, so there are two errors in this computational fluid dynamics. Upon that, you might have modeling error also in very complex physics problems. So when you compare with experiments, you can never get a correct solution. Okay, with CFD, I mean 100% accurate solutions with experiments you can never get. Okay, this is the reason. If somebody gets the 100% accurate, don't know how they have got. Okay, so because there is always truncation error, there is this algorithm error, that is you are finding solutions through iterative schemes, and there is modeling error also. Okay, some physics might be left out or something like that. Okay, so that is why you have very approximate solutions, I would say. Finally, you saw some acceleration techniques also for these iterative algorithms which we discussed. Okay, so what were the acceleration techniques mainly discussed? There was only one, I think, as far as I saw, the acceleration technique. So as to speed up the convergence of iterative algorithms. Divyendu, you want to tell something? Over relaxation, yes, exactly. Apart from that, okay, you saw, I think, alternative direction implicit scheme. Okay, so that was also one way in which you went through only half time step, that is not time step, I would say iteration step, k plus half, and then you made a sweep in the other direction. Okay. Why convergence is an issue in direct method? See, some of the matrix systems, it's not the convergence, I would say exactly, it's not convergence, but it's the solution which does not exist for some matrix directly. Okay, when the solution, when the matrix becomes indeterminate, or when you have some rows or columns where there are some zeros in inappropriate places, the matrix becomes indeterminate in nature, and sometimes you do not land up with the correct solution. I mean, you don't get the solution. It's not the convergence, because convergence does not arrive anyway in the direct scheme. Okay. Yeah, solution does not exist. Exactly. It's not convergence if the solution does not exist. Okay. So let us start with the questions. Okay. So the first question is yeah, you can change the matrix and then try to do it, but again the computational power required will be very large. So usually we go with the iterative schemes. Okay, so let us come to the first question. Which factors affect the convergence of a numerical scheme? Yeah, again this comes on the convergence. Okay, convergence means you take some initial guess for particular temperature, say, then you kind of do iterations, you find the final solutions. So the question asks, what are the factors which affect the convergence, the way in which you get the final steady state solution. So what should be the answer according to you guys? I want all of you to reply. Okay, so at least this thing. Okay, B, C, and C. Some people are telling. Okay, what about others? You can take a guess. No problem. Okay, so mainly people are going with B and C, and I see A, B, C also. Okay, B and C. Okay, fine. Okay. Okay, so let us see. First, let us come to P, and then come to C, and then come to A also. Okay, so first of all, it's the boundary condition. You already know that if you have a different boundary condition, say for example, if you have a constant temperature at all the four walls, which you can see here. Okay, you get a solution wherein you do the iterations and you get one particular solution. Whereas if you are going with a different boundary condition, say for example the right boundary condition is insulated, so you have dt by dx is equal to 0. So completely the temperature at this boundary is also changing with respect to the iterations. Okay, so that is why you need kind of more number of iterations in general to reach a steady state value. Okay, because this temperature is also changing, whereas here it was fixed. Okay, so again the solution keeps changing because this temperature is changing with respect to iterations, but ultimately it will converge to one particular value, no doubt about that, but in general it might take some more number of iterations. So that is why the convergence is different for different boundary conditions. So definitely a type of boundary condition is correct, and you should note that it's not the result which they are asking, it's the convergence. Okay, so like the number of iterations which it takes to converge and how fast is the convergence, regarding that the question is, it's not about the answer, I would say. Okay, then grid resolution also, you have seen in the weekly content that when you kind of increase the number of grid points to a very large value, it takes more number of iterations. Okay, to kind of converge to a steady state. Okay, so and it takes more computational time also. Okay, although the solutions might be more accurate. So grid resolution is also one thing. What about the initial value? See, initial value, I will give you two different situations, okay, for this first problem which I have discussed here, okay. We have constant temperature at all the boundaries, okay. Now, I have to solve this Laplace equation, del square t is equal to 0. Now one thing I can set the initial conditions as say all the temperatures at these internal grid points marked by this black circle. Okay, I'll set them to 0 and then find the iterative values. That is one approach. Otherwise, the other in the second approach, I will give the initial condition as the average of these four boundaries. Okay, in these internal cells, which will converge first. Will they converge? I mean, at the same iterations. Can you write down in the chat box? I hope you have got my question. Okay. So please let me know in the chat box whether they will converge at the same iterations, or if there is a difference, what will be the difference? If I take a 0 initial condition against average of 4 walls, average value makes faster convergence. Faster convergence means it takes less number of iterations. Yeah. So that is why initial value is also important. Okay, so most of the people were writing B and C. Okay, so A is also important. It also affects the convergence. So the answer should be A, B and C. Okay, so let us move to the next question. I want you guys to be with the pen and paper for this question. Okay, we will try to solve it. Okay, this is very important question, I would say, because ultimately you have to write a computer program for these questions. I mean, when the grid becomes very large enough. So first, before doing that computer program, you have to understand by solving it on a pen and paper. Only then will you be able to write a very good computer program. Otherwise, you will start debugging and you will not get the bug in your program until you know the basics very. I mean, the fundamentals are strong. Okay. Um, yeah, it will take time. We will try to solve only couple or only three questions. Okay, and let me tell you, it will not take more time. Okay, this question asks determine the temperature at the center of the plate using a CD4 scheme if the temperatures at relevant grid points are given in the figure below. Okay, so they have given the temperatures. Okay, you have to find the temperature ij. Okay, all the other temperatures are already given. You need not do any Gauss Seidel algorithm here. Okay, you need to do only one equation you need to solve. So the approach here is that you take the first governing equation, which is del square t by del x square plus del square t by del y square is equal to 0. So you kind of discretize it using the fourth order central difference scheme. Now I would say again that if any formula sheet is allowed in your exam, then it is quite good that you write down the formula in your formula sheet and then take it. Okay, but if the this thing is not given in formula sheet, you have to derive it using Taylor table. Okay, don't try to remember this because you will do a mistake somewhere. Okay. Okay, so figure is not visible. Which figure is not visible? Let me move my screen. Okay, this figure. Okay, yeah, it might be because of your resolution also. Okay, that's why it might be blurred. Wait, let me check with my send resolution in Google Meet. Okay, check your resolution also from your side because that might be also an issue, but I'll check from my side also. Video send resolution. Okay, I'll make it high definition. Okay, now it should not blur. Yeah, check your resolution also from your side. That might be outside. Now I am sending it in a high resolution, so resolution should not be there. Okay. So once you write down this equation, you can just copy this equation for as of now. Okay, but in the exam you should be able to derive it using Taylor table. Okay, so you have these indices in the x direction I and in the j direction we have y. So del square t by del x square, which is written as txx, can be written like this. Now what you need to do is just find this tij. Okay, so all these values are already given, so it is you need not do any iterations here. Okay, so you can find the value for Txx by just substituting the other temperature values. It should be a pretty simple exercise. Okay, so you kind of get up with this equation. Now similarly, can you do solve this for Tyy and let me know what should be the equation? See, there also you will get 30 Tij. Okay, 30 Tij will come because it will be there in the y direction also. And the delta x and delta y are same, zero point 0.2, zero point 0.2. So 0.48 will anyway come, 12 delta x square, 12 delta y square. Can you tell me the value of this? You can just take a calculator and do that. Okay, I mean, see, x direction, this is the x direction. Now y direction, just add this with suitable coefficients. Can you write the answer on the chat box? If you don't do this, then you will not understand. That is the issue. Okay, so we have to do it. For Tyy, I can similarly write the equation. Okay, Ti comma j minus 2, I comma j minus 1, I comma j plus 1, and I comma j plus 2, which is this y direction. Okay, which I am showing here. So you just need to add these temperatures, okay, with suitable coefficients plus or minus whatever is there. Okay, and then let me know the value of this particular 16,200 which I am getting for Txx. What will you get in Tyy? Can you write on the chat box? It should be very simple. See, you will write, what will you write? Minus 300 plus 16 into 434. Okay. Uh, Plus 16 into 690 plus minus 900. If you just type this much in calculator, that is what I am asking you to do. Okay. You guys don't have calculator or what? Okay. Let it be. So if you do that, you will get. Okay, one guy has answered really good. Okay. Uh, okay, you might have divided it, I guess, by 0.48. That is why you are getting 34,000. Yeah, it is correct. 34,996 exactly is correct. Okay, good. Uh, so, but I have tried to keep it the denominator as it is. Okay, I have not divided it. So you will get like something like 16,784 minus 30 Tij divided by 0.48. Yeah, if you divide by 0.48, you will get that 34,966. Yeah. Okay. Just try to see this. Okay, it's just this in the y direction, minus 300 plus 16 into this temperature. Okay, whatever is there. Okay. So Prashant has, I think, got the right answer. Okay, so now you just add this and equate it to 0. What should be the value? So there, how much I had got? 16,200. Now here I am getting 16,784. Denominators are same. Okay, so just remove the denominator. I want Txx plus Tyy is equal to 0. Put the denominator on the right hand side. You will get 60 Tij is equal to 16,200 plus 16,784. Okay, so Tij should be exactly 547. No, I got 549.73. Okay, so yeah, 547 is also a close answer. Okay, good. So yeah, so the closest option which matches here is 550. Okay, so I think that should be the correct answer. Just a second, it is not working. Okay, so that should be the correct answer. Yeah, you might get somewhere in between that range. Okay, anyway, the options are very far enough. Okay, so hopefully that should not cause a problem. Correct answer should be B. Okay, let us move to the next question. This is also a very similar question. Okay, the values are just different here. Okay, so what should be the difference in the temperature at the center of the plate by using both central difference second and central difference four schemes? Okay, now I would not ask you guys to solve for both. Okay, I don't want the final answer also here because my final answers are only not matching with the options. Okay, let me be very truthful. Okay, so I want you guys to calculate the temperature using this CD2 scheme. It is very easy, na? CD2 scheme, you know, it is very easy. You just need to add these, okay? 365 and 655. It will be like Ti minus 1 plus 2 into Ti, okay? Plus this Ti plus 1. Okay, sorry, Ti minus 1 minus 2 Tij plus Ti plus 1. So you need to find Tij. So you just need to add these two things here. 365 plus 655, one part. The other part is this second thing, 450 and 700. And also here the delta x and delta y are different. So you can divide it by whatever delta x square is there. Okay, 0.04 and 0.01 delta y square. Can you do this through central difference 2? I am telling. Just use central difference 2 CD2 scheme and let me know the temperature values. Okay. If you are finding these things difficult, na, okay. So let me try to solve with you also, so that you will get some confidence. Okay. Okay. Central difference 2 schemes. We have say Txx plus Tyy is equal to 0. Okay. Sorry for this handwriting, but I hope you understand this. Okay. So what will happen is that you kind of get into this Txx. You have two x values. Okay. You have 365 and you have 655. Okay. So you just add them up. What will be the thing which you get? Okay. Yeah, this will be uploaded anyway. Don't worry about this. Okay. Uh, so can you tell me what will be just this thing? The 365 plus 655. Okay. Just can you write down that in the chat box? Because my calculator is far away. Okay, let me just write down 365 plus 655. Okay, minus 2t divided by delta x square 0.04. Similarly, you have to write minus 2t divided by 0.01 delta y. Okay, in the y direction, what do you have? You have 450 and you have 700. Okay, you just add those things, 450 and 700, whatever is there. 450 and 700 and equate it to 0. Okay, now at least can you guys write down the answer for t? See, this much I have done. Now it should be easy. I mean, 562. Okay, one answer I have got. Okay, 562. Okay, fine. Let me see. Second order. Yeah, I have also got 562. I think yes, correct. Okay, 562 you guys have got. At least this thing should be easy. Okay, 562 you will get central difference 2. Okay, similarly you can do with central difference 4 also, like how we did earlier. Okay, so then you should measure the difference. Okay, so when I measured the difference, I was getting 1.2 degrees Celsius, which was not there in the options also. Okay, so let me. You can try this on in your home afterwards. I mean after the class. Okay, and I will ask you in the next class. Okay, I'll ask you whether you got the any of the options from this or else 1.2 degrees Celsius only as a difference. Okay, 562 is anywhere for CD2 scheme. Okay, That is correct. But for CD4 also you guys calculate it, okay, and then you can let me know. Okay. I have attached. I will be attaching these solutions also. Okay. In the this PPT will have the solution. You can go through it. Okay. So let us go to the next question. So a solution is said to be converged when. So what should be the correct answer for this? Iterative results equals the exact solution. The iterative result from different boundary conditions are the same. Iterative result for two schemes are same. Okay. Or two consecutive iterations result in approximately same value. What should be the answer for this question? Can you guys write down in the chat box? D. Okay. What about others? I want all the students to write down. Okay. Even though it might be wrong, it will let me know where you are finding issues. Okay. So that is why I asked you to write down, because last the question also many people had written B, C. Initial value many people had not written. So that is why I explained more on initial value. So that is why I asked. Okay. That is why I asked you to write down on the chat box. Okay. Two answers have got D. Yeah, so D is the correct answer. So see, basically when you say that the solution has converged, that when the solution has reached to a steady state, you have two things. Okay. uh, One is the local convergence and the second thing is the global convergence, which you have studied in the class also. Okay. So uh, between two iterations, okay, at a particular grid point, okay, at a particular grid point, the difference between two iterations, if it goes below certain minima, then you say that the solution is converged. And similarly you check for all grid points, that is local convergence. Okay. What do you do for global convergence? Can you write down in the chat box which error do you calculate? Here you are just calculating absolute difference. Okay. What do you do for global convergence? D is the correct answer anyway for this. So anyway, you cannot get uh, exact solution in iterative approach, which I have already told. And if you have two different boundary conditions, you already know that solution will be different. So B is also not the correct. And iterative ski results of two schemes will always be different. Okay, that is also not the correct. So D is correct. But what I ask is uh, global convergence. How do you determine which error do you calculate? RMS value, sorry, convergence, but with two different grids. Two different grids also you will get two different answers. Okay, you will not get the same answer. Okay, so that is not the way in which you calculate convergence. Root mean square iteration error. Yeah, exactly. You calculate RMS. So that is how you kind of calculate the global convergence. Okay. Yeah, so I hope that you have understood. Okay, so mainly what we do as CFD people, this is just my personal experience. We do calculate the local convergence only. Most of the cases, we check at every grid point. Okay, and then we take the maximum of the difference of error. So for one grid point, you will have error something like 0.01. This for second grid point you will have 0.02. So whatever is maximum we will take that and we will check whether it is less than epsilon. And a very important thing is how do you determine this epsilon value? I will give you two situations. Okay, you have flow inside a channel, a straight channel. Okay, fluid flow is there. So you have at the exit you have fixed a pressure of 0. Okay, and at the inlet you have 0 pressure gradient. So in that case you will obtain pressure values somewhere between say minus 100 to 100. Assume that you will get minus value something like this. This is one situation. Okay. Now the second situation is you have set the exit pressure to be 80 mmHg, like in biomedical cases we usually see that 80 mmHg we set. I mean not 80 mmHg, it actually varies from 80 to 120 mm. So something like, it's a very big value. In pascals if you see it comes 16,000 pascals. Okay. So exit pressure is 16,000 pascal. So you don't know inlet, inlet you give zero gradient. You get pressure values very large in the inside the domain, like you get somewhere between 12,000 to 20,000 pascal values. So how do you determine epsilon? Do you know any ideas? See, in first case I can set epsilon to be 10 raised to minus 6. If the pressure difference between two iterations goes below 10 raised to minus 6, I say that it will stop. But in the second case, it will never go below that 10 raised to minus 6. Values are going in ones and twos there, 16,001, 16,002 Pascal. You cannot go into 10 raised to minus 6 convergence criteria. If you said that your time taken will be like in months, okay? Percent of what? 1%? What do you mean by 1%? I did not get. What do you mean by 1% error? I mean, do you check with? You might be talking about relative error. Yeah, I got it. Okay. So you check with the Fij cap. You divide with Fij cap and multiply with 100. That is the error which you are. Okay, pressure value at outlet. Okay, you can fix the pressure value at outlet also, and otherwise there is another thing called relative error. Okay, wherein you take this Fij k plus 1 minus Fij k divided by Fij k plus 1. Okay, so into 100 you do that. That is also a good strategy. Yeah, exactly. That is a very good strategy, I would say. Okay, but there is something else also which we can do. Okay. What we usually do is we non-dimensionalize these values. Okay, so it is very important to non-dimensionalize the value for this purpose. Now, how do you non-dimensionalize the pressure? Do you know? You might have taken fluid mechanics course. Do you know how you non-dimensionalize the pressure with what variables? Can you write down on the chat box if you know? How do you non-dimensionalize the pressure? So if you don't know, let me tell. Okay, yeah, exactly. Pressure in Navier-Stokes with rho u square. Yes, exactly. So you non-dimensionalize it with rho u square. Okay. So every thing will be having some non-dimensional form. Okay. So you try to see p I j at kth plus one minus p at kth iteration divided by rho u square. Okay. That should be less than some epsilon value. So that you can set as 10 raised to minus 6. Okay, it will be constant. Okay, that 10 raised to minus 6 will be constant. So now what happens is that in these cases usually the density will be high with water if we are dealing with blood if we are dealing. Density is 1000, velocity is also in order of 1. So then what it becomes ultimately, it becomes delta p less than 10 raised to minus 3, which is achievable. Okay. So in that way also we can do. Otherwise, as one of you suggested, uh, you can also take the percentage also. Okay, percentage relative error it is called as. Okay, you might have not studied it, but that is also a good concept. Yes, good. So these are the two things. Okay. So again, the next question is also very similar to the previous question. What is the formula to ensure that local convergence has been achieved? Okay. So again, this is pretty straightforward, which we discussed just now. It should be option number B. Okay. The difference in the value between two iteration, it should be less than or equal to also to epsilon. Okay. Not only less than it, if it is equal to also, we stop the iterations in the computer program. Okay. So yeah, B should be the correct. Now let us try to see only one or two final questions because it's already around 8 o'clock. Okay, so averaging of neighboring grid values to update the function Fij is known as what? So what do you call this as? Mainly, you do okay, in the Laplace equation you do, right? Fij is equal to 1/4 of all the other grid points. You might have seen that in the weekly content. Okay, what about others? Only one person has written the answer. Okay, mostly you guys are telling A. Okay, So yeah, so that particular method is called as relaxation, but you have also something called as under relaxation, over relaxation, which they might have written here as overshoot and undershoot because it leads to values which go below or which go above, okay, than what is actually there. So that is why overshoot and undershoot terminologies are used, okay. So the correct answer should be relaxation. So let us see normal Gauss-Seidel method. You do this, okay. You average with the neighboring cells in the normal Gauss-Seidel approach. Now you do under relaxation in the following way. So you can subtract Fij at the kth iteration from both LHS and RHS, and you can rearrange that. Okay. So you just come up with Fij at k plus 1 is equal to Fij at k plus the average. Okay. So what you see is that in order to make this Fij at k plus 1 close to k, you kind of multiply this by some omega factor, which is called the relaxation factor. Now in the under relaxation, what we do usually is that we take omega less than 1, okay, and then calculate Fij k plus 1. In the over relaxation, we take greater than 1 but less than 2, okay, it should be less than 2, otherwise it will diverge, okay. So that is done, okay. So that is under relaxation and over relaxation. So these things are very important when you actually write a computer program, okay. The main idea behind these things is to make you uh, more confident to write the computer programs based on these algorithms. So that is why you need to solve the problems, okay. Especially the question number 3 I have asked you. I'll ask you in the next class again what is the answer which you got, what is the difference in the values, okay. I will upload these anyway, the PPT, okay. um, Now last question, let us see. It is about the convergence rate. So we have three different schemes which are given here: Jacobi iteration scheme, the line Gauss Seidel, and the point Gauss Seidel. Okay. So you might have studied this in weekly content anyway. So which one do you think is the fastest? Which is intermediate and which is slowest? Write down on the chat box. Okay. Which is fastest? You can write down first. Okay. Which is the fast? Which solution gives you? Which scheme gives you the fastest convergence? Jacobi is slowest. Yes, Jacobi. What we do is that when we go on to calculate the k plus 1 value at say second grid point, we still take the kth iteration for first grid point, kth iteration value. Whereas we already have the k plus 1th iteration value for the first grid point. We can take that, but we do not take that in the Jacobi, okay. So that is why it becomes very slow with respect to convergence, Jacobi, okay. But in Gauss Seidel we do that. We have the k plus 1th iteration value at first grid point. So in second grid point when we are calculating, we take that only updated value directly. So it is faster. But what about point Gauss Seidel is given. It's not point SOR. Okay, it's not point successive overreaction. That is not discussed here. We are discussing only three schemes: point Gauss Seidel, line Gauss Seidel, and Jacobi. Okay, Jacobi is slowest. What is intermediate? I mean intermediate speed, intermediate convergence. Is it line Gauss Seidel or point Gauss Seidel? Okay, let me ask a question. Line Gauss Seidel is faster or point Gauss Seidel is faster? Can you write down on the chat box whether line Gauss Seidel is faster or point Gauss Seidel is faster? I've got only one answer till now. Okay, I'm just listing those methods here in my presentation. Okay, Jacobi, point Gauss Seidel, line Gauss Seidel. So in the line Gauss Seidel, what we exactly do is that we kind of in one direction, okay, say in the x direction, we use the tri-diagonal matrix algorithm to get the values at one go. Okay, even in just one go, we are calculating all the three values, f I minus 1, I and I plus 1. The other values we just put it in the B matrix, okay. So this is semi-implicit in nature. It's not implicit, it's not explicit also. So because we are taking some values at k plus 1 something. Okay, so this is the fastest amongst the three. Okay, live Gauss seidel, because we are calculating the results at one go. Okay, uh, so that is why you should guess that this should be the fastest converging scheme. Okay, because we are not calculating one by one, wherein some communication error might be there. Okay, which will happen. Okay, that is why Jacobi was slowest. Okay, now this here we are ensuring that three values we are calculating simultaneously, so the convergence is faster, but computational time might be large because you have to implement TDMA algorithm. The computational time might be large, but the number of iterations to reach the convergence is less. Okay, in line Gauss seidel. So convergence they have asked, so that is why line Gauss seidel is fastest. Now if you see the question, then statement 1 is false because it is telling Jacobi iteration method converge first. So that is definitely false. Statement 1. Statement 2, line Gauss seidel method converges faster. Yes, that is true. So statement 2 is correct. That is true. So B should be correct. Okay, for this particular question. Okay, so let me just end the session for today. If you have any queries with respect to these questions, you can ask now. Okay, and these PPT and the YouTube, I mean this recorded video will be uploaded on YouTube. Okay, so if you have any doubts, you can go through the video again. Okay. There are some other questions also which I had thought solve 8, 9 and 10, but you can see them on the PPT. Okay. Hi, can you briefly explain how to go about the derivation for CD4 discretization for Laplace equation? I mean derivation you are asking with respect to what? With respect to Taylor table approach? Is that? So I had told you that you should derive if you are not given a formula sheet. So you are asking for that derivation because last week we had discussed the Taylor table approach wherein you can calculate the discretization. So let me just brief through it. Are you asking that? Yes, yes. Okay, Taylor table approach. Okay, okay. Let me just briefly explain that. Okay, see, you want fourth order central difference scheme. Okay, so what you should have it in mind is you should have a stencil with four neighboring points. Okay, see if you have Tij, you have should have four neighboring points for fourth order accuracy. Okay, and it is central difference. Okay, so in the back direction 2, in the front direction 2. Okay, so this is I minus 2, I minus 1, I plus 1, I plus 2. Okay, so now you have to form f dash in such a way, f dash is equal to sum a into f of I plus 1. Okay, just let me write it in a proper way. Okay, so f dash at I is equal to a into f of I minus 2 plus b into f of I minus 1. Okay, plus c into f of I comma j. Okay, similarly plus d into this I plus 1 plus e into this. Okay, so this is the way in which you write. Now once you write this, okay, formulation, you should form a Taylor table using this. Okay, so what you do in this Taylor table is see, you have to first write this f of I minus 2 whatever are there here. Okay, in the rows, f of I minus 1. Okay, then you should write okay, you should write f of I, f of I plus 1, f of I plus 2. Now this you should write in the rows. Okay, now in the columns you have to the way in which you express f of I minus 2 using the Taylor series, you know, you should be able to express this as in terms of f at I, then f dash at I, f dash at I, f double dash at I. Okay, and f triple dash of I. Again, since you need four unknowns, okay, you can restrict yourself only to four columns. Okay, since you need four unknowns, number of unknowns is equal to number of columns. Also you need f dash also. Okay, f dash. So this you can write it in terms of Taylor series expansion. This coefficients, you know how you can calculate. F of I minus 2 is equal to yeah, so for Laplace it is f double dash, I agree. So f double dash also you can formulate it in a similar way only, okay, Taylor table, okay. So what you do is that you ultimately need f double dash is equal to a into f of I minus 2 and these things. Instead of f dash you have f double dash here, okay. That's the only difference, okay. You can construct it in a very similar manner, I would say. Instead of f dash which I have written at the last, you should write f double dash, because you ultimately need f double dash, okay, is equal to some coefficient into I minus 2, some coefficient into I minus 1, okay, f double dash. Okay, so here you have f double dash, so here it will become 1, otherwise it will become 0 1 and 0. Okay, yeah, RHS, yeah, that is why I took F double dash here. That is why I have written in the fifth row I wrote F double dash. I did not write F dash here. Okay, there is a reason why I did not write F dash. Okay, only F double dash. Okay, then you expand it using Taylor series. Okay, whatever coefficients will come here, you write them down. Okay, for I minus 1 Taylor series, the same thing. F double dash 0010 because only F double dash is there. Okay, so in that way you write down, and then what you should do is multiply this by a, multiply the second row by b. Okay, now what you get is four equations. Okay, you should add all these things: a into f of I minus 1, a into b into f of I minus 1, and c into f of I. Okay, when you add these, you will get something like this, or whatever is there here. Okay, a into f of I minus 2. Okay, and finally f double dash multiplied by minus 1 because you have to bring it to RHS. Okay, and then you will finally get this. Okay, this expression is equal to, you will also get some other terms. Okay, into f whatever are there, fi dash. Okay, now you add this whatever coefficients are there row wise, these coefficients you add them. Okay, write it here for fi. Similarly for fi dash also you will get some coefficient added up, fi dash. Okay, then what you have to do is you will get four, since you have four columns, you will get four equations to solve them, get the abcd value. Okay, so that is the way in which you use the Taylor table approach. It will take some time, it will take at least around 10 minutes if you do it properly on paper. Okay, so I just told you the approach. I hope I am clear with this. Okay, are there any other queries? Okay, if not, then we can leave the class. Okay, if there are no other queries, just let me check once again. Okay, thanks. Thank you for joining. Okay, bye.